All right, so last time we kind of did a summary of what would be the class, what we'll be covering in the class. So today let's start with chapter 1. Which is the introduction and conceptual definitions. Okay, so our job today is nothing really complicated. It's just to start getting used to the vocabulary that we'll be using throughout the semester for other problems and to understand the material. Okay? So, like we said the other day, the main example we need to use here, the main example we use generally is the water. So we know the water is a substance, but that the substance water can be found under different forms, no? Like liquid, solid, or gas. So how do you define all that stuff? So first definition, we just said water is a substance, okay? So what is a substance? So I try to give simple definitions. So we say that a substance can be anything, but that is defined, and that a substance can be at different states, no? But that the different states are defined by the values of the properties. So let's say water, oil is different substances that will have different properties. So maybe an easy definition for a substance will be a substance is defined by its properties, okay? Each substance will have specific properties. Okay, so let's do that. So a substance is defined by its properties. Okay, and this could be density, etc., etc. Okay, so now maybe I introduce another term. What is a property? Oh, I like this black. What could be a property? So obviously it's kind of coming over here, but a property is like density, no? So a simple definition could be to say what? Like a property is like a physical characteristics that defines the substance, no? But let's say it's a physical characteristic. So I use a blue. The property is a physical characteristic of a substance. I mean, or you can remove the substance of anything. So we say density. What else could be? Viscosity, whatever you want, okay? Even pressure, all kind of stuff. All right, so now thinking about the water, we have a substance that is defined by its properties, but we know that we can find the substance water into different form or what is called different states, okay? Liquid, gas, or solid. So let's say a state okay, so substance water defined by its properties can be found at different states. but we know that the densities, we know that the properties of the one substance at different states will be different, no? The example we gave last time is that if you put a bottle of liquid water in the freezer, what's going to happen? It's going to expand and probably break the bottle, no? That's because property density is different for ice than it is for liquid water. All right? So let's over here. A substance can be found at different states. So let's say liquid, solid, gas, okay, or vapor, that will have different properties. So again, if somebody throw to you liquid water, you're gonna get wet, but it's not a big deal, no? If somebody throws to you a cube of water, of ice, you might get hurt, no? It's still the same substance, no? Okay, and then what else can I think of? So when you go, for example, from liquid water to, let's say, to ice, when you go from one to the other, it's called a process. Okay, so let's say a process So a process, oops, the blue. A process is when a substance goes from one state to another. Okay, and really, I mean, here I give the drastic example, like let's go from liquid water to vapor or liquid water to ice, but it doesn't have to be a completely change of state, because even if you have cold water, even if it's liquid, cold water is different, a little bit different than hot water, no? Both of them can still be on the liquid state, but they will have slightly different properties, no? Okay? I mean, not that drastic, no, but they will have different slightly properties. So it's not that you need to go from one state to the other. It's just like if there is a variation on the initial state of the substance you are doing. It's also called a process, okay? So we have different type of processes. A process can be defined as isothermal. What could be another one? Isobaric. Isochoric. Let's see what else can we have. Adiabatic. Still thinking. Polytropic. I'm probably missing some, okay, but I'm trying to. And maybe some more, okay, but that's probably covered most of them. So what does isothermal means? Isothermal means constant temperature. Isobaric means constant pressure. Isochoric is the one that is a little bit hotter. That means constant volume. Adiabatic, maybe you know, that means constant. It doesn't mean constant, sorry. It means no heat. So you don't add heat or remove any heat. And polytropic means that it's follow the relation, the ideal gas relation, PV to the gas relation PV to the K equal to a constant. This is the polytropic gas relation. It's not the ideal gas relation. But so, for example, what is K? K is the gas constant. K is a gas constant that basically is defined on how this gas compresses. So, for example, for air, it's about 4.2, but for different gas will be different, no? So all the different gases do not compress the same way. All right. Okay, something I forgot to mention about the properties, which again is not that important, but it's just vocabulary or semantics will be finding throughout the course. Let's see, properties. So a property okay, so there's two types of properties. All right, then let me give the names and then we try to define which one is which. One will be extensive. It's not that important to understand, to remember the words. It's important to understand that there are two different types of properties. And intensive. So for example, let's look at this class. All right, let's look at properties. Let's say somebody asks you to find what is the total mass in this class. So you could say, okay, we can ask everybody's mass. We can go and weight every single chair, the tables, and we can add all of them together, and we get the answer, no? Okay. Or somebody can ask you what is the total volume of this classroom. You can take a meter, or you can take, a cube. You can take a box. How many boxes can you get into this room? And you know the volume of the box. You multiply it, you find the total volume of the classroom. Okay. So this is one type of property. The other one now is that if somebody asks you what is the total temperature in this classroom, are you going to go and take the temperature of each one and add it together? No. So you see those two types of properties are different, no? Let's say mass and temperature. So one is like the summation of all the parts, like what would be the weight or the volume of the class, let's say the weight. And then the other one, that would be what is the temperature, or let's say what is the pressure inside the classroom, is more a property that is global, no? That depends on the whole medium, all right? So let's see which one is which. So the extensive is the first case, is the summation of all the individual parts, okay? So summation of all individual parts So this could be like the weight is equal to weight 1 plus weight 2 plus so on, no? Okay, or the volume. And an intensive is something more like a global property, and an example would be the temperature or the, let's say, the pressure. Okay, so right now the only important thing is that you recognize that you can have different type of properties, extensive or intensive. Later on, I hope you will realize that when you will go to the tables to find what is the state or to find the value of a substance, no? You're always gonna have to look, you're always gonna need one extensive and one intensive property, okay? In most cases, okay? No, in every single case. So you need one of each, even though you don't realize it, but this is the important part, okay? Like for example, when you do pressure and volume, what is the ideal gas constant? PV equal nRT, no? So let's say you know, if you know T, yes, you're gonna have to find, you need to find T in function of P and V, no? P is what? Is it an intensive or extensive? It's an intensive, it's a global, no? But the volume will be what? It will be an extensive, all right? Now let's say you have, if you want to find the pressure will be in function of the temperature and the volume. And again, the same thing, no? The temperature will be global or intensive, and the volume will be extensive for the summation of all the parts, no? Okay? So, and it's like that every single time. So when you go to the tables basically what they do is solutions of equations that we are not solving, okay? But one will be extensive, the one will be intensive. Okay, the other property we're going to be talking about, I think we talked a little bit last time, would be temperature. Okay, so here, nothing complicated. So we know the temperature is an intensive properties, but here what's important is that we know we have four different scales for temperature. So we have here, so let's say this will be the Celsius, this will be the Kelvin, this could be the Fahrenheit, and then this could be the Rankine. Okay, so let me write it down. Celsius, Kelvin, Fahrenheit, and Rankine. Okay, and we know that generally the reference for these scales, if we use the water, what would be the reference values for the Celsius? What is the one will be for hot? You will have the boiling, of water is 100 degrees Celsius. Then generally for cold, you will use the freezing temperature of the water. So this is really the two important ones. And then, I mean, this is not that important, but if let me put it in red, this is not really one of the reference. What would be the absolute zero? So will be is 273.12, I think it is, but just use this one. So this is the scale in Celsius. Now, what is the difference with the Kelvin? The Kelvin, what happened is that the absolute zero is 0. The 0 degree Fahrenheit would be 273, and then the boiling would be 373. So now for the Fahrenheit, so Mr. Fahrenheit, what did he choose in order to have his scales? So basically in this one, Celsius used water, no? Boiling temperature of water and freezing of water, okay? What about Fahrenheit? What are the two measures he used? What was his reference for cold? Okay, so cold is 32. What happens at 32? So wait, so this is, be careful because this is not really, that wasn't his reference really. His reference was 0. But be careful because this 0 means something different. What is the difference between 0 degree Fahrenheit and 32 degree Fahrenheit? It's funny, like, I always think that everybody knows that, but not that much, okay? Go ahead.
Isn't Fahrenheit supposed to be based on how people perceive temperature?
No, actually, the thing is that what happened is that for him, he tried to choose as the reference temperature stuff that he could encounter easily, okay? So 32 degrees Fahrenheit is the temperature at which pure water is going to freeze. 0 degrees Fahrenheit is the temperature at which salt water is going to freeze. Okay, that is the difference. Okay, so for him, his cold reference was really what temperature is the ocean going to freeze? 0 degrees Fahrenheit. Okay, and it's salty. So if you want, this is salt water freezes, so salt, and this would be pure water. I don't have much space. I'll put it here. And really, the absolute 0 is it's minus 459 point something, but let's say minus 460. And then I know you know that. The boiling point, and I need to add one more. Boiling point is 212. Okay, so for Fahrenheit, his reference was 0 degree Fahrenheit is temperature at which salt water freezes. And he needed to find a high value, now a high value for the hot, to define hot. So what do you think you can find that is something pretty stable? Now you get it every day measure. What is it? What about the body temperature? Body temperature is to be pretty stable, no? Okay, so Fahrenheit, what he used is 100. And really it's not 100, but it's whatever, 98, between 98 and 99. What he wanted to use is the body temperature. Okay? So, you know, to me, I always say that English or customary units sometimes make a lot more sense than metric, okay? They use stuff that they see around them. Okay, now, so this is the Fahrenheit, and the equivalent in Fahrenheit will be 0 degree Fahrenheit will be minus 460. So then this one here will be the 32 becomes then 492, no? 460 plus 32, 492, and the boiling will be 672. And I'm not going to put the other one. If you want, you can do the other one. This will be what? 470. And this would be 460, no? All right, so you have all these equations on the tables, but how do you go from Kelvin how do you get Kelvin from Celsius? So you know it would be what? Temperature in Celsius plus 273 How do you get the temperature in Rankine's from the Fahrenheit? Is temperature in Fahrenheit plus 460. And now this one is more difficult. How do you get the Fahrenheit from the Celsius? Is 1.8 T times the temperature in Celsius plus 32, okay? And you can work out the units for all of them on the reverse order. All right. Next. Throughout the book, almost every single problem, they will tell you to find specific values, okay? So let me first define something that is called the specific volume. So what does the term specific means? In thermodynamics, basically means that specific volume, we use lowercase v, is equal to, and I use this v with a bar for volume, but you see it's a capital or an uppercase V divided by M. So let's say this will be volume. This is the mass. And this is the specific volume. So I'm really here, I'm just gonna put it here very quick. You realize that maybe the specific volume is really equal to what? It's just the inverse of the density, no? Yeah, correct. We see that in a few weeks, we're gonna use that relation, but we don't need it yet. Okay, so here what's important is that you see the term specific basically means per unit mass. What is a specific volume? Is the volume per mass. Okay? And I'm going to define two more now that we haven't seen, but I want you to see the notation. Lowercase specific value generally are denoted by lowercase u equal to capital U divided by M. U is used as, so this will be, is the symbol used for the internal energy. So lowercase u will be specific internal energy. Now let's say I have this H, little h would mean what? Capital H divided by M, no? Where H, you don't know what that is yet, but this will be the specific enthalpy, okay? Sometimes they will ask you in a problem, or many times they will ask you in a problem to find the specific work. What would that be? Work divided by the mass, no? So basically the term specific means you need to find the results per unit mass. Okay, next we're going to look at another property called pressure. So pressure generally is defined with the letter P, and is equal to what? Force over area, or you could say P equal to force over area, and the units could be what? Newtons, meter square. Most of the time in English, units will be PSI, but could be LBF, foot square, no? They have different options. Okay, and other options. Okay, so is pressure, do you think is a strong force or there is no strong pressure? Pressure can be pretty strong, no? And we're going to find out now with one example. Okay, so this is what is called the Magdeburg, which is a city in the, I don't know if it's Austria or Germany, I think it's Austria, Magdeburg hemispheres. And the exhibition was on the 17th century on 1654. All right, so let's see what that is. So if we come here, Magdeburg hemispheres. Okay, so basically Magdeburg hemispheres is what you see over here. You have two cylinders, all right? And now you join them together, and through a little pump, you create inside here the vacuum. Okay, so if you create the vacuum, what's happening is that this hemisphere is going to be attracted to this one, no? All right, they're going to be. All right, so what is the force that is needed in order to separate these two hemispheres? Okay, so I have here an example, but if you can check the values with me as we do it would be good. All right, so, and I think this is the original values. So we have the two half hemispheres over here with the hook. I try to do the same figure more or less that they have that we just saw. Okay, with the hook. So let's say this will be the area. So they have exactly the same area. So the diameter of each hemisphere is about 50 centimeters, which is approximately, let's say 20 inches. Okay, approximately 20 inches. All right, so now you put them together. Create vacuum, I guess, with a pump. Basically, the pump will be doing what? Removing the air from the inside. Okay, so you create this, and now you're gonna end up with your 2/2 hemisphere this way. Okay, so we know that the pressure inside is 0, and then outside it will be surrounded by the atmospheric pressure. And the question is, what is the force that you need in order to separate the two hemispheres? Okay, so this will be, if you want, our free body diagram. And now we need to do to find the force. We do summation of forces. This is static. Now, which force you're going to be able to separate this equal to 0. So what will you have? Whatever is external will be 2 times F, the force, should be equal to what? To whatever is happening over here, no? On the inside. So what would this be? It would be P atmospheric minus P inside times the area, no? Does that make sense or no? Do I need to explain this more? Pressure times area is force, no? Okay, if you look at this figure, this force over here, one here should be equal to the change in pressure times this area. Yeah? It's not twice the area because now you put them together over here, no? Yeah? All right. So that means that from this expression, we find that the force needed, or the force that would be equivalent to the vacuum created inside, should be equal to what? P atmospheric. And what is the pressure inside if it's the ideal vacuum? 0, no? So in the ideal case, the force that is needed should be equal to the P atmospheric times the area divided by 2. Okay? So that should be the value of the force. All right, so using SI units, let's do the calculations. All right, so let's see, the area, this area over here will be equal to what? Pi r squared, or what would be the same? Pi d squared divided by 4. How big we say was the diameter? 50 centimeters. So we know that 50 centimeters is what? Is half a meter, no? Okay, so we have A will be equal to pi over 4. You will have to do calculations for me. I don't have all these details calculation. 0.5 squared. Okay, I don't have the results. So this is one thing that we need. Now the other thing we need is P atmospheric is equal to what? Is equal in English units is 22.92 inches of mercury. All right. Or 1 bar is equal to what? 101.325 kilopascals. Okay. So what is this equal to? This is equal to 101.325 10 to the 3 what? Newtons meter squared, no? All right, so let's go and do the calculation. Let's substitute back into the equation over here. Okay, so we're gonna have F, let me just rewrite the equation, equals to, just had it here, P atmospheric times A divided by 2. We're gonna have that F to be equal to what? So we have P atmospheric that is equal to 101.325 times 10 to the 3. And this is newtons meter square times pi over 4 times 0.5 square. This will be meter square. Divided by 2. So I have here a number, but go ahead and check. Please, the number I have here is that this is equal to 9,947.5 newtons. And this is approximately, I have here as well, about 2,236.3 lbf. All right, so is that a big force, 2,236 pound force?
Yeah.
It's not bad, huh? All right, so let's see in a horse, how many horses would that be? So we need to know how 1 horsepower was defined. So 1 horsepower. So, I mean, I don't think I need to do this, but 1 horsepower is defined as the power what is power? Is force times distance, no? So it's the power required to raise or lift, let's say raise 75 kilograms, which is approximately 165 pounds. Why 165 pounds? Because when they developed this, that was the average weight of a person, of a man, okay? Men were a lot shorter than what they are now, right? 165. So to raise 75 kilograms, 1 meter, which is approximately 3 feet. And if we need power, okay, so work will be force times distance, and power is work per unit time, no? So you will do that in 1 second. So how much power do you need in order to raise 75 kilograms, 1 meter in 1 second? And you can do a calculation, it's not that complicated, but you find out that 1 horsepower was found out to be equal to 735.75 newtons. Okay, so let's see how many horses do we need it. So number of horses, so HP needed to pull apart the hemispheres. So we know the force is 9,947.5. If we divide that, so this is if you want, this is if we divide by 735.75, I think you get, I don't have the exact result, but for I can see on my notes, you probably get 13 point something. 13.52, but since you cannot have 0.52 horse, no? All right, you're gonna need at least 14 horses. And is that 14 horses, so 7 on each side, or is it 7, or is it 14 on each side? It's 14 on each side. So you see that a little ball over here in this sphere of 20 inches requires a pretty good amount of force to pull apart, no? So the important thing is that you realize that pressure is a very strong force that you can use. Yeah? Okay? So, all right, so now we're going to start reading the first chapter, which will be here, chapter 2. First principle of thermodynamics. Okay, so just one quick thing is not important again, it's just semantics of words. In the textbook, they use first law of thermodynamics, I use first principle. Reason being is not important at all, it's because to me a law in engineering is something that, or in physics, that you cannot prove, no? You cannot derive. Newton's law is given to you, no? All right? And all the different laws are given to you. A principle is something that is derived from a law, okay? And since the first principle is derived, I call it, since the first law of thermodynamics is derived, I don't want to call it law, but principle. But who cares about principle or law, no? All right, so here we go. So what is the title of this class? Thermodynamics. So what is the starting equation? So the whole class is this. But you're gonna see that by the end, in about 10 weeks, it's gonna look completely different. It's gonna look different already today, okay? All right, so this is the starting equation, no? Thermodynamics. We need to mix that with what? With heat. What is thermodynamics? The study of the motion of the heat. All right? So let's say we have here starting equation. Newton's law. So I can write over here summation of forces equal to ma. Yeah, I'm gonna have time. Now you can write this as what? M dV/dt, because you know that the acceleration is the derivative with respect to time. And now I'm gonna remove, if you want, the variable time or use the chain rule. This should be equal to dv let's say ds dt, where s is position vector or distance. So what is the velocity? Is distance divided by time, no? So you want to put, you can put over here little bars over here, ds dt, ds. So what is ds dt? This term will become the velocity. This is basically the derivation of work and energy. The principle of work and energy is exactly the same derivation. So we get summation of forces equal m times v dv ds. So what type of equation is this? This is a differential equation, no? You have dv, this will be dv dx, they are variables. What is the first thing they teach you in differential equations when you need to solve a differential equation? Is that first step is to separate the variables, okay? So what are the two variables you have over here? V and S, no? So let's move S to the other side. So we're gonna have summation of forces ds equal to m v dv. Now that you have separated the variables, you can go and integrate in order to solve. So let's say if you integrate, we're gonna get over here summation of forces ds equal to the integral of m v dv. So let's leave the left-hand side untouched as summation of forces ds. And now let's integrate the right-hand side between, let's say, v initial and v final. What will be the integral of v dv? Will be v squared over 2, no? So really this term over here becomes what? 1/2 m v squared final minus 1/2 m v initial squared. Okay, what is the physical meaning of this term? What is 1/2 mv squared? Is kinetic energy, no? So really the meaning of this term here is change in kinetic energy, or what I can call delta Q sub E. And what is force times distance? This is work, which is force times distance, okay? And I can call, let's say I can call this W. This should be page. Okay. Or I could rewrite this equation, let's say as equal to change in kinetic energy. Okay, and we just say this term over here is work. Okay, so now I'm going to find 3 different terms for work over here. So this expression here, work, let's say this will be work 1. This will be work done by something known as conservative forces. Work done by conservative forces. Then here we're going to have a W2, which is just be work done by, let's just say, all the forces. And W3 would be work done by friction forces. Okay, we have 8 minutes, so let me start maybe backwards. First one we're going to look is work 3. Work done by friction forces. So this is going to be very quick, and the other one, the work 2, W2 is going to be quick as well, and then work 1 we'll leave it probably for next time. Okay, so I think we kind of talked about it the other day a little bit. For any force that is friction, is it easy to calculate the work? The answer probably is not. But what happens if you have any friction force? Let's say you rub your hands one against each other, or you rub your hand on top of the table. What is going to happen? You're going to generate heat. Okay? Is the heat easy to measure? Yes. And you agree that the amount of heat that you generate should be proportional to the amount of work that you're doing with your hand, no? Okay? So I think about any force that creates heat, even if somebody slap you, okay? What does that create on you? Probably you're gonna get in a bad mood, but in addition to that, whatever you get hit, it generates heat. Yeah? When you throw something against the wall, let's say a ball against the wall many times, what's happening to the ball? It gets hot, no? Yeah? So impacts also generate heat. So it's not only friction. I mean, to throw something on the wall is some type of friction, no? Doesn't need to be just rubbing, it can be also an impact, okay? So what we're gonna say is that the work done by any frictional force, we can say that should be proportional to heat. And the letter used for heat is Q, where Q is heat. Okay, then W2 over here. Work done by all the forces. Most of the time, if not 100% of the time, this will be pressure. Okay? If you have a piston, what is doing force in the piston? What is creating work in the piston is the pressure, no? That's how engines work, no? The pressure moves the piston up or down a certain distance, so that creates work, okay? And if you calculate per unit time, that's become power, all right? But let's just see over here, work done by pressure, all the forces, Johnny will leave it as just a general W. And the work one over here will be the work done by conservative forces. All right, and I'm going to stop over here because this is going to take more than 4 minutes. All right. Let's stop over here.